The Earth has provided humanity with multiple natural clocks that measure the passing of time. Each method of absolute dating is able to observe different lengths of time, ranging from individual years to a few billion years. Each method is unique, and each come with their own challenges and flaws. After dendrochronology, luminescence dating has the next furthest sight, stretching as far back as 1,000,000 years into the past. Luminescence dating is a broad field with multiple different methods of achieving dates. Some methods have only recently been developed, and some have persistent problems plaguing the science, leading to dates consistently having as much as a 10% margin of error. But understanding how luminescence dating works, and why it sometimes doesn't, requires context. The story begins with atoms, the tiny building blocks of the universe. Every element in the universe is made of atoms. Atoms consist of a nucleus, made of positively charged protons and neutral neutrons, surrounded by rings of negatively charged electrons. The outermost ring of electrons is referred to as the valence band. Electrons orbit in multiple rings, with greater number of electrons allowed to inhabit each ring depending on the mass of the atom and the energy levels of the electrons. Because electrons have certain energy requirements in order to stay within their ring, the introduction of more energy into an electron can cause it to either be elevated to a new ring farther from the atomic nucleus, or be outright ejected from the valence band, becoming a so-called free electron. Without any interference, a single element will always naturally have the same number of protons and electrons, but they can have variation in the number of neutrons they possess. These differences in an element, sometimes called different species of an element, are known as isotopes. Hydrogen, for example, has 3 isotopes. The lightest hydrogen isotope only has 1 proton. The second, called deuterium, has a proton and a neutron, and the third isotope of hydrogen, called tritium, has 1 proton and 2 neutrons. Typically, the lighter elements have an equal amount of protons and neutrons in their nucleus. When an atom has a certain ratio of more neutrons than protons, like in the case of tritium, the ratio interferes with the force that binds the atom together. In order to regain stability, one of tritium's neutrons transforms into a proton and an electron. This process changes the atom from the unstable tritium to a new element, the stable isotope helium-3, which possesses 2 electrons, 2 protons, and 1 neutron. When a radioactive element decays, as the neutron morphs into a proton and an electron, it also releases a subatomic particle. This highly energetic particle is violently ejected from the atom, and impacts the electrons of other atoms until it itself loses energy. The initial energy of the subatomic particle is so great that it essentially blasts electrons out of the valence band of the atom. An atom that gains or loses an electron is known as an ion, and the radiation responsible for stripping an atom of electrons is called ionizing radiation. In living tissue, this process damages the molecules in cells, which can eventually lead to mass cell death. But in a crystal like quartz or feldspar, electrons behave slightly different. All crystals form an ordered repetitive structure called a crystal lattice. In naturally occurring quartz or feldspar, the lattice structure can commonly be disrupted by trace amounts of other elements trapped inside the crystal during its formation. These impurities create small pockets of negative energy. The free electron falls into the negatively charged deviation in the lattice, and a positively charged hole is formed in the valence band it originated from. When the crystal is unburied, the photons, which are particles of light, from the sunlight immediately energize more electrons, resulting in more free electron production. When 2 energized electrons collide, one of them loses energy and emits a photon, and one electron is pushed further away to eventually collide with a different electron. This chaotic process eventually reaches an equilibrium, wherein all the holes are sealed and all electrons have recombined with an atom, even if it isn't the atom it originated from. This process of recombination releases light, which can be observed in a lab environment. This is the core of luminescence dating. The light that is released during electron-hole recombination directly correlates to the length of time that the crystal was buried. There are 4 types of luminescence dating: thermal luminescence, infrared stimulated luminescence, infrared radiofluorescence, and optically stimulated luminescence. Each method is used on different minerals and can measure different ranges of time. All methods of luminescence dating use the same calculation to determine the age of an object. The age of an object is equal to the equivalent dose of ionizing radiation, divided by the yearly dose rate of the sample. The equivalent dose of ionizing radiation is the estimated amount of radiation the crystal was exposed to, measured in grays. A gray is the equivalent radiation absorption of 1 joule of energy per kilogram of matter. The equivalent dose is determined by observing the intensity and duration of the light given off by the crystal when it is thermally or optically stimulated. In essence, this equation is dividing the total amount of radiation a crystal received while it was not exposed to light or heat by the rate of ambient radiation exposure every year. After an equivalent dose sample has been stimulated and the luminescence has been observed, scientists expose the now neutral crystal with a so-called regenerative dose of radiation and subject it to stimulation again to see how the crystal responds to a known quantity of radiation. This is done multiple times with many different subsamples. The original, natural luminescence profile is charted on a graph alongside the data from the other samples and regenerative doses. The equivalent dose is the point on the graph where the natural luminescence intersects with the average curve of all of the lab-generated data. The yearly dose rate is achieved by taking additional samples from the surrounding environment. The dose rate can be simply determined by using radiation detectors on the surrounding soil, or by manually measuring the amount of uranium, thorium, rubidium, and potassium in the soil. Once the equivalent dose and dose rate have been determined, the age of the sample can be calculated. Every crystal has a saturation limit, where ionizing radiation will no longer significantly affect the atoms inside of it. The yearly dose rate, therefore, directly ties to the maximum age of a sample. The lower the yearly dose rate, the longer it will take before the sample reaches its saturation limit. This also means that samples found to be at their saturation limit could very well be older than what scientists can determine. For example, quartz crystals close to their saturation limit have been found in some cases, but not all, to underestimate the age of a sample by as much as 10% when measuring ages greater than 100,000 years. An important aspect of luminescence dating is that it is commonly cross-referenced with radiocarbon dating. If there is organic material in the same layer as a quartz crystal, both dating methods can be used to calculate the age that soil layer was deposited. If the ages reached independently by radiocarbon dating and luminescence dating agree, meaning they have considerable overlap with each other, then it could be reasonably inferred that the age of the crystal is between the minimum and maximum of the two given dates. And inversely, if one of the dates is far off from the expected age, it would prompt a reevaluation of both methods. Infrared stimulated luminescence can be used on quartz and feldspar, but feldspar performs better under this method than any other. True to its name, it uses infrared light to stimulate electron recombination. IRSL can selectively detect feldspar even among other minerals, which makes it useful if a scientist was unable to extract it from a matrix. With this method, quartz has been dated to 153,200 years, plus or minus 14,200 years. In comparison, feldspar has been dated as far back as 600,000 years. IRSL seems to consistently overestimate the age of samples by a slight margin, nearly 5%, but feldspar is consistently more accurate due to the natural presence of radioactive potassium inside it. The decay rate of the potassium can be measured and compared to the expected dose rate to achieve a far more accurate equivalent dose and dose rate than in quartz. Infrared stimulated luminescence spawned another method called infrared radiofluorescence. This field is extremely young, only being devised in 1999, and has not seen much use due to commercial limitations with acquiring the machines necessary to perform experiments. Unlike the other methods of luminescence dating, which are technically a measure of the rate and duration of electron-hole recombination, IRRF is a direct measure of the number of trapped electrons inside a crystal. More research is necessary on the method, but it has shown promising results in a lab. IRRF can process crystals with a far higher saturation than other methods of luminescence dating, potentially in excess of 700,000 years. Thermally stimulated luminescence uses heat to encourage electron recombination. This method is one of the most commonly used, and can potentially determine dates as far back as 1 million years. Thermal luminescence involves heating a sample to a certain temperature, over a certain duration, depending on the type of crystal being tested. The thermal profile of quartz shows different information than regular optical stimulation. After the initial test, the crystal is heated an additional time to compare the luminescence profile. The primary benefit of thermal luminescence dating is that it can provide accurate dates with material that has been bleached by the sun. The thermal profile survives bleaching as long as 20 hours, while the optical signal typically lasts no longer than 2 minutes. Optically stimulated luminescence is divided into 3 categories based on the color of the light being used to stimulate luminescence. Blue light is used on exclusively quartz, green light is used on feldspar and quartz, and red light is used on specifically volcanic feldspar and any quartz. The crystal lattice structure of every type of crystalline solid is slightly different from the next. The pattern of the lattice affects the placement of impurities within it, which therefore influences the positioning of the negatively charged electron traps. Certain wavelengths of light are better suited to penetrate deeper into a particular crystal based on the crystal structure, and therefore are better suited to stimulate electron recombination in particular crystals. Blue light OSL can be used to reliably date sediment as old as 100,000 years. Information confirming the age range of green light and red light OSL is scarce, but both are seemingly also used within the same range of 100,000 years. Luminescence dating is based in sound science. The behavior of atoms when exposed to ionizing radiation is well understood. The methods used to reach dates are directly correlated to known and observable quantities of radiation, and the number of viable methods of luminescence dating overlap with each other and with radiocarbon dating to successfully date objects nearly 1 million years old. However, there are multiple challenges within this field of study that invite scrutiny. These issues do not invalidate the science, they simply require careful navigation to surpass. Dirt and soil are dynamic materials, constantly being affected by wind and water erosion, human activity, and a mixing process known as bioturbation, which is caused by burrowing animals. Rivers pull sand and soil from their banks as their trajectory drifts over time, transporting loose sediment, which exposes minerals to sun and water. Natural disasters like volcanoes, tsunamis, or landslides also play a significant role in erosion. These events may expose old soil, causing the radioactive signal of long-buried crystals to be bleached by the sun. Bleaching can reset the clock, resulting in a significant underestimation of the age of samples. Long-term water exposure can limit the yearly dose rate, which would undersell the real age of a location. In an area with volcanism or even human activity, exposure to extreme heat over 100 degrees Celsius could interfere with the radioactive dose of quartz and feldspar crystals. The saturation limit of a crystal can also report an inaccurate date if the crystal reached its saturation limit thousands of years before it was discovered by humans. Feldspar anomalous fading is a mysterious phenomenon thought to be related to quantum mechanical processes occurring within the crystal. This strange behavior results in feldspar luminescence giving dates that are short by 5%. Despite this challenge, an estimate of the rate of anomalous fading can be used to predict the real age of a sample, with a much smaller margin of error. With luminescence dating, mankind's view of the past can extend far beyond the first civilizations. Unseen mechanisms within the very soil have allowed scientists to peer back into far distant days, long before the dominance of mankind. Luminescence dating granted humanity the ability to learn about the environment hundreds of thousands of years into the past, even before the evolution of Homo sapiens. Luminescence dating is an invaluable science that will only become more refined as time progresses. But there are other methods that can see just as far into the past, potentially further. Rather than relying on crystals in the soil, or the dead wood of ancient trees, one method of absolute dating uses shell and bone as its clock, to measure the passage of time since the decay of long-dead animals. Thank you for watching. This video was far more complicated in its scope than the previous, so please let me know in the comments if there was anything that I should explain further. Unlike dendrochronology, information about luminescence dating is harder to come by. Much of the available research is centered around blue light optically stimulated luminescence and thermally stimulated luminescence. At times I came across two papers that would directly contradict each other, and there is a lack of information about methods like infrared radiofluorescence and green or red light optically stimulated luminescence online. Some of the topics in this video were simplified for brevity. For example, radiation produces different types of particles depending on the mass of the decaying atom. The different types of particles aren't exactly relevant to the story, only the impact of radiation on atoms in a crystal lattice. Also, as mentioned, feldspar anomalous fading is a strange quantum tunneling behavior, but quantum mechanics isn't just beyond the scope of this video, it's beyond my ability to explain in a satisfactory manner. Let me know in the comments and I can make a follow-up video explaining or correcting myself. Also, please let me know if you prefer background music or just my voice. Until then, the next video will be covering a simpler topic, amino acid racemization dating. I won't promise an official release date, but that video will come out within a month from now. Thank you all so much for watching, and I will see you in the next video.